Just a quick reminder before we get into the lesson to download the hands-on lab exercises that accompany this complete CCNA course. I'll include the link in the description. Also remember to subscribe and hit the notifications bell so you don't miss any of the lessons in the course. Okay, let's get into it. In this lecture, you'll learn about the private address ranges. These were documented by the IETF, that's the Internet Engineering Task Force, in RFC 1918. RFC stands for Request for Comments. So when the IETF release some documentation, they release it as an RFC number, meaning that other engineers can comment on it and maybe suggest improvements. But the RFC is still a finished standard as well. So the final standard, as of today, for private IP addressing is RFC 1918. There are a load of other RFCs out there as well for pretty much every technology, but if you asked me to name an RFC number, then the only one that I probably could is RFC 1918 for private addresses. Because if you're in conversation with somebody, it's quite common to call it an RFC 1918 address. Sticking with our theme of how the internet was originally designed to work. Private IP addresses were originally for hosts that should not be connected to the internet. Because obviously if you're an organization and you've got a part of your network that you don't want to be connected to the internet, you're not going to pay for public IP addresses for those hosts. That would be a waste of money paying for IP addresses that are never going to be used. So a way that you could save money is by using private IP addresses on there instead. The other benefit you get from it is that the hosts are not going to be connected to the internet, so it makes them more secure as well, and it locks down that they can't talk on the internet. So if you're thinking, well, why would anybody ever do that? Maybe it's a highly secure environment, like maybe it's a bank, and the bank has got a part of their network that they want to keep completely off the internet for security reasons. They would use private IP addresses there. Another possible example is maybe you've got a high school and they've got PCs there, but the school authorities don't want the kids to be able to get on the internet. Again, they would use private IP addresses there. So the addresses that are private, there's a range in each of the different classes A, B, and C. In class A, we've got 10.0.0.0 to 10.255.255.255. And that uses the standard class A subnet mask of /8. So we can also write it as 10.0.0.0/8 or 10.0.0.0 with the subnet mask 255.0.0.0. The class B private range is 172.16.0.0 to 172.31.255.255. That is 172.16.0.0/12. So the class B range does not use the default subnet mask of /16. And the class C range of private addresses is 192.168.0.0 to 192.168.255.255. So the class C range uses, again, it's not the default mask, it uses a /16, which is the normal default mask for a class B network. Okay, so those are the three ranges of private addresses. You want to have these committed to memory. So just like you're going to commit to memory what the range is for class A, class B, and class C, also remember what the ranges are that are used for the private addresses. This is not just for the CCNA exam. You're expected to know this off the top of your head when you're working in the real world as well, because you'll see that RFC 19 addresses are used a lot in the real world. I'll get to the reason for that very soon in this lecture. So let's look at an example of where we would use private addresses back in the day when we wanted to keep our hosts off of the internet. So this is a secure environment. We've got Bank A on the left, we've got Bank B on the right. Bank A have got a public part of their network that is used for their staff who are allowed to access the internet. That's at 175.11.0.0/24. and then they've got a different part of their network, which is maybe where they have some very sensitive servers that they want to keep off the internet, and they put on there the private address 10.10.10.0. Bank B, their public address is 196.14.10.0, and they've also got a private range, which is 172.18.5.0/24. Okay, an example number 2, you can see that here, Bank A and Bank B are both using 192.168.10.0. That's fine. They don't have any connectivity to each other anyway because they're on completely separate networks. So you'll find that with private addresses, loads of organizations all over the world will be using the same private address ranges. They can't use the same public address ranges because they need to have connectivity to each other over the internet. But the private addresses don't have any connectivity outside that organization, so those addresses can be reused over and over again. Okay, let's revisit the IPv4 global address space problem. So the designers of IPv4 did not realize how big the internet was going to get. And when they first designed the IPv4 format, they thought that 4.3 billion addresses is going to be more than enough for what would be required. But the problem is, we know today that 4.3 billion is nowhere near enough. So another problem is that the protocol is not efficient in the way that it allocates addresses as well. Again, because they thought that they had more than enough addresses, they didn't worry about wasting addresses. For example, the 127 address, wasting an entire class A range just for loopback testing. Also, the way that large address blocks were given out to organizations who were not using anywhere near as many as the actual addresses they were given. So the IPv4 address space, it's not big enough for how many addresses we actually need on the internet today. So they ran out of addresses. So quite a while ago, in fact, back in the late 80s, they realized that they were going to run out of addresses. So they started working on a solution to the problem. And in the 1990s, the solution that was developed was IPv6. So the addresses we've been talking about up to this point in the course has been IPv4. IPv6 addresses have got a different format, where IPv4 addresses are 32 bits long, IPv6 are 128 bits long. But the address space is not just 4 times as big as the IPv4 is, it's actually exponentially bigger than that because we keep doubling it every time we add a bit. And the IPv6 address space is actually 7.9 times 10 to the power of 28 times as many addresses as IPv4. So there's a huge amount of addresses with IPv6, and it was developed in such a way that they should never run out of addresses again. But there's also a problem with IPv6, just like there was a problem with IPv4. And the main issue is that there's not a seamless migration path from IPv4 to IPv6. So if you're an organization, you've already got your host deployed and you've got IPv4 addresses on there and you've done all of your IPv4 addressing design, it's not easy. You can't just flick a switch and convert that to IPv6 because the address format is completely different. It's not seamlessly backwards compatible with IPv4. So it's quite a big project to migrate from IPv4 to IPv6 if you're already an existing organization. So because of that, NAT, Network Address Translation, was implemented as a temporary stopgap before everybody could convert to IPv6. And the way it works is an organization can use those RFC 1918 private IP addresses on their inside network, which are not publicly routable, so they don't work on the public internet. But what they can do with those addresses is on the way out, they can convert them to the public IP address on the outside. So if you're using a private IP address on the inside, whenever you communicate with anybody out on the public internet, when the traffic gets to them, it looks like it's coming from a public IP address, so they're able to send the traffic back to you. And many hosts on the inside, so many hosts on the inside using those private IP addresses can share a few or even just a single public IP address on the outside. So let's have a look and see how this works. So you see we've got Office A on the left, and they've bought a small range of public IP addresses, which is 175.11.0.1/28, which gives them 14 addresses. And they're using the private addresses on the inside of 192.168.10.0/24, and they've got 200 hosts on the inside. Well, they're able to convert or translate those private addresses on the inside to the public addresses on the outside whenever they communicate with anybody on the internet. So if we didn't have private addresses in that, they would have required 200 public IP addresses for those hosts on the inside. But now they're doing it with just 14, and actually they could have done it with just one if they wanted to. So by using private addresses in that, this saves loads of addresses in the IPv4 public address space. It also saves organizations money as well because they don't need to pay for those public IP addresses. Thanks for watching. If you'd like to get the complete course ad-free right now, then you can enroll in my CCNA Gold Bootcamp by clicking the link above my head or in the description. It also includes full study notes, quizzes, and 150 pages of additional troubleshooting labs you can't find anywhere else.